Well, hello everybody. It's Liv, and today I just want to show you something real quick, okay? So this is a little bit of an improv kind of thing, okay? So all right, I decided I was not happy with some of the way that my parsing is working. I needed some advanced way to detect patterns within within a source file and being able to just automatically create a tree out of that, right? So after much thinking about it, I came up with what is basically a language, a very small language. The definition file is actually 800 lines. Well, that's a little bit of a lot, but actually not so much. It must be a lot less in terms of source lines of code, because as you can see I have lots of padding in here with white space and whatnot. So yeah, it's actually not that long, right? And what's a langdev? Well, it's basically a little system built within Automat, which is one of my projects, which kind of lets you define what's the syntax of your language, basically. And I'm extending it so that it will allow, you know, it will allow you to more or less have a little bit of an interpreter within Perl. So, just putting this out there, not ideal, right? So we have an interpreted language, and running an interpreter within an interpreted language, bad idea, bad idea. Um, so hopefully we can ship this with a compiler so that yeah, your code can just be written into a binary, and it will execute much faster. But just to get this project off the ground, for now what I'm doing is I'm just running the interpreter within Perl, right? So that's basically that. Um, but still, it's not quite that much of a full-blown interpreter, because much of what it's doing is just passing code references around, which would actually be quite fast, okay? Or at least in as far as I've been testing, it's kind of fast. So okay, how does the PLPS work? So first and foremost, PLPS stands for Peso Language Pattern Syntax, right? So language pattern syntax. So this is designed to grab values that you've defined for your language. Let's see if I have the language definition for C open somewhere around here. No. Okay. So let me just open that real quick. Okay, so langdevs c.pm. Okay. And within the langdev file, we have this list of keywords, right? List of keywords within different categories, and I will explain the categories some other time. But for the most part, you have types. It's self-explanatory. Type specifiers, or or just specifiers, because sometimes it's a little bit more complex than that. But for now, it's that. Then intrinsics, and I'm not entirely sure what goes and doesn't go in an intrinsic, and what is an intrinsic and what is a directive. Like when you start categorizing keywords like this, you just come into what's very much philosophical questions of what is the true nature of something. Uh, I'm not so much interested in that. This is just for now. It might change, it might not. Then flow control, right? And this one is really hard to get wrong, right? So if, else, for, while, do, switch, case, default, anything that just moves the instruction pointer around, that's flow control, right? So anything that has to do with jumps and conditionals and all of that, that's flow control. Then we have a reserve. So this is basically for everything that is a keyword but doesn't fit within the other categories, right? So you could put null in here, right? So because that's something that you would usually want that name to be reserved. Okay. And well, and a bunch of few other things that don't really come into play at this moment. But you get the general idea, right? So we have a list of keywords. What PLPS does is it takes first and foremost a language definition, and in this case we say it's C, and this this path, let's call it that, this path in here would actually hook back into a Perl module, right? So a value within Perl, okay? And because langdef, once you call the init in here, it will just register the module like so, right? So the name you give this language, you will have it from here. And so then now you can do lang c types, and that will give you a list of all your types, right? Or rather a hash containing where the keys are your types. And then you can store additional information about the types within that hash, right? So what PLPS does is it says, okay, so tell me how to get the object where all your definitions are. And so we say in name of your object, and that's that. Okay. Then we have beg and end, and beg simply says here begins a pattern, right? And so we give this classification. Pattern is just like general usage. Then we give it a name, right? Then we can use there's basically two kinds of tags. This is how I call them, tags. And this would be like a smaller pattern, right? And the way we do is, we have a spec for specifiers, type for types. All right, so bear, this is for bear word, which would basically be any valid name, right? According to what the language itself has defined as a valid name, right? So you cannot get this wrong. You absolutely cannot. Then the second type is it's strings, right? So we can write the short strings, say, I don't know, something like something crazy, I don't know, right? And this is essentially the same as doing this. It will just copy paste it as it is, and so you could write a regex in here, I suppose, right? Something like this. You could do something like that, right? You could try. And then give me a second. So once we declare the pattern, we can just use it. As you see here, I define the cdecl pattern. So this is basically looking optionally for a type specifier, then a type, then the indirection level, so a bunch of asterisks, and then a name, right? So this is basically a C declaration. I can just copy and paste this in here, and it will expand into this expression. And so it will look for that pattern of C declaration. Then ODE means opening delimiter. So basically, it's this. But it could also be this, and it could also be this. So a little bit of a hold up of the system. I suppose the better way would be to do it like this. But for now, I'm doing it like this. The tilde in here means that if you match this pattern, do not report it, right? So do not print it out. So basically, don't add this. If you match this, continue. But if you do, if you match this, continue. But do not add this token into the resulting syntax tree, right? Then the modulo simply assigns a name to the pattern, right? So like an alias, right? So here we don't want to get the asterisk as is. We want to call this indirection level, and so we add this little thing in here. Then the question mark is, this thing is optional. It doesn't need to be there. If a tag is not optional, then if you don't match, that's that. The execution stops, there is no match, right? And so if it's optional, question mark. Then the plus simply means keep matching, right? So if you match once, keep matching until you find something that doesn't, and then move on. Then for now, the final operator we have is the minus minus, and what it does, it's called rewind, right? So, and I'm using it here so that if we match a comma, we want to go back and find another C declaration, because this is where we're matching the arguments of the function, right? And so if there is a comma, that means we have to go back, match another C declaration, right? And that's that. And once again, because we do not want the comma to be reported, we just nullify that with the tilde. And we're calling this CS list for comma separated list. So this will not be visible in the tree, but it's just a nice thing to to give it that alias, so that it's made clear that what this token is doing, what this tag is doing, is converting this into a comma separated list of arguments, right? So that's that. And then finally CDE, which is just closing the limiter. So in this case, it will be any of these three. So again, here we could replace it with this. It would be the same. So all right, I have a little test file written in here, in which, well, little bit of a long story, but I've made it so if you have within the PLPS directory, you have a file written. If you have a file with these language patterns, the langdef will load it automatically, and then you can call that program basically, because this distills down into a set of functions that will let you match any of these patterns that you declared, right? And so basically, we call that program and we tell it, hey, verify if this string in here matches a cfunc declaration, right? So this is this pattern right here. All right, and so let's see. All right, so I need to go into get match, and this is basically a function that's taking the matches gotten by running the pattern tree. It takes that and it gives you a set of nodes, right? So let's actually just show you the tree as is. So that's breach, okay. And let's see, yeah, okay. All right, and so our expression was, and this is just nonsense I wrote to test it out. So it's int pointer var, which doesn't make sense, static const int pointer x and const int pointer y, right? And we get here, and okay, we get first and foremost at the top the name of the pattern that we try to match, and then wait a minute, this isn't quite right. Give me a sec. Right. So I don't know. There's something wrong with the new lines. Whenever I break something into multiple lines, it sort of ruins the pattern. I have to look into that, but I'll do it later. Anyhow, as you can see here, the first cdecl pattern I renamed to func, and so what we get here is func. So this is like the first element within our tree. Func breaks down into a cdecl, which is a specifier, type, indirection level, and name. In this case called var. And here we have specifiers. There are no specifiers, as we can see, no type specifiers. Then we have type int, and that's that. Then for the indirection level, a single, and then the name is blah, right? So quite simple actually. Then we have args, which is the second cdecal, right? So we said match the parentheses, but do not report it. And here we have the parentheses. If I take this out, and I'll show you, but if I take this out, then we wouldn't have a full match. Okay. So we have the arguments and we have the specifier, and first the first type specifier that we got, and because we are doing the rewind, we get as a second leaf the value, the type specifier for the second element, right? Then again for type we get int and int, right? Because it's int here and int here. But for the indirection level we get 2 asterisks and then 1, because again we've used pointer and pointer. Okay, so as you can see, this is actually quite simple, but it's a cool thing. So this is a very small, very simple language. I still have to work out some of the details, but as you can see, it's somewhat functional, right? It works. It just works. Okay, so can we do some zooming in onto the tree? Well, as it turns out, yes. I've written some utility functions to do this kind of thing. So for instance, suppose we only want to look at the arguments, right? We have this function called branches in. So basically it will look at a node tree and give you the branches that the branches whose value matches this regular expression, right? And so if you want args, we know we only have one, so we can take this list and just take the first value, right? So let's say args, and then we can say args bridge. If we knew we would have more than one branch matching this, then we would just take the full array and just iter through it. I'm not going to do that right now, but you know. Okay, and as you can see, now we only get the arguments, right? So right, it's a very simple thing, but it makes my life so much easier. It's unbelievable. How come I never thought of this before? So anyhow, we can do the same thing for the function, right? And let's actually change the name, because let's call this slice. Why not? All right, and what do we get? We get the value, the field relating to the function, which is this one right here, which again is just a cdecal, but yeah, it's a cdecal with extra steps, so to speak. Anyhow, yeah, I guess I'll show you what happens when there's no match. Actually, I'm not entirely sure what should happen, but let's see. Well, that's weird. That shouldn't have matched at all. Let me just print the whole tree. All right. So, okay. So right. So there was no match. So the function matched all right, but the arguments didn't match. Why? Because it was expecting an opening delimiter, and it found none. But here's kind of the problem. If I open it up like this, it will match. You see? So that's not quite correct. I guess what we could try is adding this, and I actually need to escape it, because this would be how do you say? This will be passed through a regular expression. So because the parentheses has a special meaning in a regular expression, I have to escape it. Same thing here with the asterisk, right? So yeah, just little things. Let's call this SOD. No, let's call it parents. Let's call it O parents. And okay, so that's a bunch of errors. What happened? Okay, so that's kind of crazy. Not entirely sure. Give me a sec. Okay. Okay, so it's failing. It's failing for some reason. Hmm. Okay, so this is weird. All right. Tell you what. Let's just do some debugging. All right? Why not? We're going to print out the program the program tree, right? So the program tree before it is built. Okay. So let's see. Right. Okay, so here's fine, and all right. So here's the problem. Okay, so it's how this thing has been interpreted. Right. Right. Okay, so I can fix that. Give me a sec. All right, so this is because the modular has like special meaning, right? This is what happens when you have a character be reserved. Once you start passing it through regular expressions, things tend to break. But don't worry, we can fix this. Right. So this is not quite right, but because I actually need to capture this, right? All right, there we go. That would be nice. Co-parent. Okay, so I think that should solve it. Let's try. All right. So apparently yes. Okay. So we could do the. Let's see. If we change this for a bracket, now it doesn't match. Perfect. Okay. So let's just do this for both. Okay. Because in this case it's a function declaration. We do not want to match uh, just any delimiter. We want to match the right delimiter, right? So, once again, okay. So these are just things one has to deal with, you know. So let's see. Okay, so this one is weird. So this happens because I'm converting the strings into these cute little tokens so that I can remove spaces and things like that without messing with the strings, you know. Here it has broken in a way that did not expect would happen. That's interesting. Not entirely sure how did this happen. Okay, so that's really weird. Let me just check real quick. All right. This shouldn't happen. This definitely should not happen. So let's see. It's it's really weird. It's really really weird. Hmm. Okay, so tell you what, let's just caveman. Let's just caveman this thing, okay? Not going to be pretty, but that's fine. All right, so okay. What I'm gonna have to do is kill the parser at the time of mangling, okay? So what I have to do is do this, just exit so that doesn't give me so much noise. All right. Okay, so it's a little bit uncanny. It's a little bit uncanny. Because at no point, at no point is this thing put into the numerical field. So how did this happen? Oh, somehow the format was corrupted, is what you're saying. Right. Right. Because of this symbol, right? So so this is actually kind of crazy. This is actually pretty fucking crazy. Uh, I don't get uh, how did the format get like stamp itself in here? Oh, no, right. So the format is not being right. Okay, right. So I know what we have to do. Okay, so this is an unexpected bug, but I'm glad this thing came up because actually I can just do this. All right, let's try that. No errors. Fine. You see, I solved it. Okay, so yeah, I'm proud of the fact that I can solve this kind of problem like no problem, And so, all right, so now it should not match when we use brackets, right? And it doesn't. Right, so perfect. Okay, so this was basically the PLPS language in a nutshell. And that's it for me. Have a good one.